projects.
Thank you very much for the introduction, and thank you for inviting me to give a flash talk. So I'll be talking about flips of dissections and their relation to silting mutation. So the setting we're starting with is a polygon, convex polygon with a dissection, a fixed dissection in it, so a collection of diagonals that do not cross. And we're going to look at other diagonals in that polygon that will link some vertices that are here, small pink squares. They will be called blossoms. There's one blossom at each side of the vertex of the dissection. And for some reason that will become clear later, I want to consider the boundary components, boundary segments joining the vertices of the dissection with the blossoms as part of the dissection. Okay. Now, in that combinatorial setting, we'll be interested in some diagonals of the polygon that join two blossoms. And not all such diagonals will be permissible. We'll only look at some that are compatible with the base dissection in the following meaning. So if we look at the intersection of our diagonal with the arcs of the dissection, this is the arcs that are crossed. We want to have a connected subset of the dissection. So this is the case here. And if the diagonal satisfies this property, we call it an accordion. So this is an example of an accordion. And here, this is a non-example. If we look at the diagonals crossed, diagonals of the dissection crossed by this one, we get two distinct components, connected components. That was a non-example. And here's another non-example. So here the diagonals crossed by this one are these. And you can see there's this small boundary component here, which is not connected to the rest. So this was not an accordion either. Around each vertex of the dissections, there are some accordions. The arcs joining the adjacent blossoms are always accordions. And those cannot cross any other accordion. And so they, with respect to accordions, they will behave like boundary components, and they're called the irrelevant accordions. Okay. So our setting is a fixed dissection in a convex polygon, and we now have a notion of diagonals being compatible with the dissection D, called accordions. And we'll be interested in maximal collections of pairwise non-crossing accordions. Those will be called maximal D dissections. So in case D was a triangulation, every diagonal will be an accordion, and maximal D dissections will be triangulations. So the notion of maximal D dissection generalizes that of triangulation. And the term accordion comes from this picture. So the arcs crossed, the arcs of the base dissection crossed by an accordion have this shape, and that's hence the term. Okay, and the theorem we are interested in was due to MacConville in a different setting, and in this setting to Garver-MacConville and Manneville-Pilaud. And it says that given a fixed dissection, the maximal D dissections all have the same cardinality. And moreover, there is a notion of a flip for these maximal D dissections. So the combinatorics of maximal D dissections resembles a lot that of triangulations. So triangulations all have the same cardinality, and there's a flip for triangulations. One small difference here is that you cannot flip an irrelevant accordion, the small ones around the vertices. Okay, so here's an example of a flip. So this is an example of a maximal D dissection. It has 6 relevant accordions, and they are not crossing each other. And if we want to flip at this accordion, we have to slide along adjacent accordions to give this new accordion. Okay, so that was a very specific instance of a flip. The general situation is slightly more complicated and can be illustrated with this flip here. As you can see, there are two ways here to slide along adjacent accordions. You could do it clockwise or counterclockwise. For triangulations, flipping clockwise or counterclockwise gives the same arc, but that's not true for general D dissections. And here we get two different diagonals, but precisely one of these two is not an accordion, and so we just keep the other one. And that's the generic situation for flips or maximal D dissections. So with Vincent Pilaud and Pierre-Guy Plamondon, we proved that this combinatorics generalizes to oriented surfaces with boundaries, mark points in the pictures, and so is closely related to representation theory of gentle algebras. With Mikhaïl Gorsky and Hiroyuki Nakaoka, we wanted to categorify this situation. And we defined a category of accordion, A, which is a home finite, Crouch-Schmidt, and additive, and its indecomposable objects are in bijection with the accordions. We proved that this is an exact category. In fact, it's an extension closed subcategory of a category of modules over some gentle algebras that I haven't defined here. And it has some very specific and really nice properties. First, it is hereditary as an exact category. So each object is the co-kernel of an injection between projectives. It has dominant dimension at least one, meaning that the co-resolution, the injective co-resolution of any projective have a projective injective first term. And also, we proved that the maximal D dissections coincide with the silting objects, basic silting objects in this category. So we've categorified the accordions and maximal D dissections using silting theory. We also want to categorify the flip, so we want some nice theory of mutation for the silting objects in this category. Yes, it turns out that the properties 1 and 2, global dimension at most 1, dominant dimension at least 1, already appeared in a very different setting in a work in collaboration with Arnau Padrol, Vincent Pilaud, and Pierre-Guy Plamondon. We were looking at some relative structures on cluster categories, and those satisfied the same properties. So we want a setting which encompasses both situations, the category of accordions and cluster categories with relative structure. And so we decided to work with X-triangulated categories. So now C is any X-triangulated category satisfying those assumptions, the assumptions similar to that of the category of accordion. So the term zero Oslander already appeared in Pinchot-Stokes, and so it means those properties, global dimension at most 1, dominant dimension at least 1. Okay, and we proved that in that setting, the silting objects, basic silting objects, all have the same number of indecomposable summands. So in the category of accordion, this recovers the fact that maximal D dissections all have the same number of accordions. And we proved that there is a nice theory of mutation for basic silting objects. So they can be mutated at any indecomposable summand, which is not projective injective. In the category of accordions, the projective injectives, the indecomposable projective injectives are the irrelevant accordions that cannot be flipped. And so this is an algebraic version of this fact here. We also proved that the two complements in the mutation can be related by exchange conflations, either in one direction or the other, but not both. And this reflects the fact that flips of maximal D dissections correspond to either sliding clockwise or anti-clockwise. So depending on which direction you slide, that gives you one or the other conflation. Okay, so this theorem categorifies and recovers the results on maximal D dissections and accordions, but it also applies to different settings. So for instance, cluster categories with relative structures, and there it recovers the mutation theory of cluster tilting objects. And there is also another setting where it applies, but that might be mentioned in Thomas Stokes later today. So that's related to almost rigid modules. Okay, and I'll end with an example of a category of accordion for a very small dissection. Thank you.
Thank you very much. Beautiful.